All right, let's dive into a world that is so incredibly small. The rules of color as you know them just, well, they get a complete quantum rewrite. We are talking about nanomaterial optics. And believe me, it's going to change how you see, well, pretty much everything.
So, let's kick things off with a bit of a puzzle. Everybody knows what color gold is, right? It's gold. But what if I told you that if you could shrink a piece of gold down to the nanoscale, it would turn a brilliant, stunning ruby red? I mean, how on earth is that even possible?
And that is the heart of our quantum color puzzle for today. We're going to unpack this whole thing and see how, at the tiniest scales imaginable, the universe seems to play by a completely different and frankly much cooler set of rules.
See, the main thing you've got to get your head around is this. In the world of nanomaterials, size is everything. It dictates an object's physical properties. It's not just a smaller version of the big thing, it's something fundamentally new.
So, what is the big secret behind this tiny phenomenon? Well, it all comes down to the size of the particles themselves. Let's pull back the curtain and look at the actual science going on here.
That secret actually has a name. It's called the quantum confinement effect. And this is the absolute key. When you shrink a material down that small, you're essentially trapping its electrons in a tiny little box. And when you confine electrons like that, their energy levels have to change. That, in turn, changes how they interact with light. And how they interact with light? Well, that's color.
Okay, the easiest way to think about this is with a guitar string. A short, tight string, right, it gives you a high-pitched, high-energy note. A longer, looser string gives you a low-pitched, low-energy note. Nanoparticles work the exact same way, but with light instead of sound. The smaller particles are like that short string. They interact with high-energy, bluish light. The larger ones? They're like the long string, interacting with low-energy, reddish light. Simple as that.
So this isn't just some abstract theory. You can actually see it with your own eyes. Let's take a look at some real-world examples that create this sort of nano-sized rainbow, all based on this one amazing principle.
All right, let's circle back to our gold puzzle. We start with the simple fact we all learned as kids. Gold is, well, it's that distinct, shiny yellow color.
But as we know now, that's not always true. At the nanoscale, gold completely breaks its own rules, and it's this brilliant, beautiful illustration of the power of the quantum confinement effect.
And here you can see the proof. Tiny gold nanoparticles, they show up as red or even purple. But it's not just about gold. These things called quantum dots are even crazier, because by precisely tuning their size, scientists can make them glow in pretty much any color in the rainbow. It's incredible.
Now this is way more than just a cool science trick. This size-dependent color is a tiny powerhouse that is already changing the technology you and I use every single day. So let's look at where this stuff actually shows up.
The key property that makes all this so useful is something called enhanced photoluminescence. Sounds complicated, but it just means these materials are ridiculously good at absorbing light and then spitting it back out. You can think of them as hyper-efficient little light bulbs, a property that, as it turns out, is unbelievably useful.
So why should you care? Well, take a look at the screen on your phone or your TV. Chances are it's using quantum dot technology. That's why the colors are so incredibly rich and pure, and why it uses less energy. And it gets better. In medicine, these same quantum dots can be used to tag and literally light up specific cells inside the body, letting us see biological processes with a clarity that we've never, ever had before.
So we end not really with an answer, but with a question. We have literally learned how to paint with quantum physics, creating colors not from pigment, but from size itself. Just think, as we get better and better at controlling matter at this tiny scale, what other hidden properties are we going to unlock? What new worlds will we be able to see with these quantum colors?